Imagine a piece of metal so, incredibly delicate that just touching it with a standard cutting tool creates enough friction and heat to warp it instantly. Welcome to this deep dive. Today we have a highly specialized mechanical engineering presentation to unpack for you, focusing on the invisible physical realities of extreme precision manufacturing.
Right, and we're tracking 5 distinct grinding techniques here. It's really a progression of scale, We're moving from brutal material removal all the way down to delicate microscopic shaping.
Yeah, going from clearing mountains of metal to making geometric adjustments you literally can't even see. So, let's start on the heavier end with creep feed grinding,
Yeah, that one is defined by a massive depth of cut, but a very, very slow feed rate.
which kind of reminds me of a glacier, like moving incredibly slowly, but
Yeah.
packing so much continuous power that it carves out a solid rock valley in a single pass.
That's actually a great analogy because when you're machining high hardness alloy steel pins, you really need that continuous steady power to efficiently clear exceptionally tough material.
So you're establishing the raw physical dimensions before getting into the finer details.
Exactly, which brings us to surface grinding. This establishes foundational precision by creating perfectly flat planes.
And the engineering application here is all about dealing with extreme tolerances,
Right.
right? Like when manufacturing complex machine housings.
Right. You need those surfaces to be so perfectly flat. I mean, we're talking deviations measured in mere microns.
Wow.
Yeah, so that when you bolt 2 pieces together, it creates a completely leak-proof metal-to-metal seal holding back high pressure.
Just metal on metal. But, it's one thing to make a static housing perfectly flat to hold pressure. It's got to be a completely different physics problem when those metal parts need to constantly move and grind against each other under load, like in a gearbox.
Oh, absolutely. Once parts start meshing, you need complex interlocking shapes without losing that accuracy. That's where profile grinding comes in.
Because the grinding wheel itself is pre-shaped to be identical to the target profile, yeah.
Exactly. It's used for stamping exact involute geometry directly onto gear teeth.
Wait, involute geometry?
Yeah, an involute curve is this highly specific mathematical shape that allows gear teeth to roll against each other seamlessly. If they don't have that exact curve, the teeth slide against each other instead of rolling.
Which I imagine generates massive friction and just grinds the gearbox to dust.
Pretty much, yeah.
But wait, doesn't all this grinding involve severe friction anyway? Like, doesn't that heat warp the metal and immediately ruin that exact involute curve you just stamped onto the gear?
It actually does. I mean, heat causes microthermal distortion during manufacturing. The metal literally expands and warps.
Oh, wow. So how do you even fix that?
Well, to fix that, engineers use jig grinding. So after a part has been heat treated and warps a tiny bit, you go in with a jig grinder, usually specifically into something critical like bearing bores.
But how does it actually correct a microscopic deviation compared to just a regular grinder?
So a jig grinder uses planetary spindle movements, meaning the grinding wheel isn't just spinning in place.
Oh, so it moves around.
Yeah, the entire spindle assembly orbits the center of the hole. It's guided by computer-controlled micro-adjustments, and it literally shaves off microscopic imperfections caused by the heat treatment.
That is wild. Restoring extreme positional accuracy. But, okay, what happens when a part is so incredibly fragile that even those micro-adjustments of a jig grinder would destroy it?
Right, like an ultra-thin flex spline.
Yeah, which is basically a highly engineered, paper-thin, flexible metal cup used in robotic transmissions.
For something like that, you'd need electrochemical grinding, or ECG. It combines electrolysis with grinding, which results in almost zero cutting force.
So if you're using electrolysis to strip metal, aren't you essentially just initiating controlled rust?
Yeah,
Like dissolving it away?
basically.
But how do you maintain extreme precision down to the micron if you're just chemically dissolving the piece? Doesn't it spread?
Well, it's heavily controlled by the electrical current. The chemical and electrical reactions do the heavy lifting, stripping away the material atom by atom to create a soft oxide layer.
Oh, I see. So the wheel isn't really cutting.
Right. The abrasive wheel doesn't actually cut the underlying metal at all. It just gently wipes that residue away so the electrolyte can keep working exactly where needed.
That's incredible. So the part doesn't even feel the cut.
Exactly. ECG is the absolute preferred method for finishing those delicate flex splines because there's virtually no physical contact, meaning zero mechanical stress is induced into the part.
Wow. So for you listening, these terms, creep feed, jig grinding, ECG, they aren't just vocabulary. They represent the hidden extreme craftsmanship that keeps our modern mechanical world functioning.
Yeah, without these techniques, modern robotics, aerospace, and advanced manufacturing simply wouldn't exist.
Which leaves us with a pretty wild thought to mull over. If we are already combining chemistry and electricity to shape ultra-thin metal with zero stress today, what entirely frictionless non-contact manufacturing methods might be used to build the impossible machines of tomorrow?